All right, welcome back. So we're going to talk about a little bit of Mendelian genetics as an example. So if you've had general biology, great. You probably remember the 9 to 3 to 3 to 1 ratio that's predicted for two traits in Mendelian genetics. And if you haven't had general biology, don't worry. Just know that there's some data out there talking about how when you cross peas together, you might predict to get specific traits and specific ratios. So for example, you might spend a whole bunch of time like Mendel growing peas, and you might be interested in testing whether the data that you get from your experiments meet the expectation of 9 to 3 to 3 to 1. And so if being round is a dominant trait and being yellow is a dominant trait and being green and wrinkly are both recessive traits, then you would expect to get ratios of 9 to 3 to 3 to 1. So 9 round yellow seeds, 3 round green seeds, 3 yellow wrinkly seeds, and 1 wrinkled green seed out of every set of seeds, out of every set of 16 seeds. So you have 4 categories in this case. And you would calculate you go out and you have your observed values. So maybe you end up with 315 round yellow, 108 round green, 101 wrinkled yellow, and 32 wrinkled green seeds. And basically then you have a total of 556 seeds. In this example, you would know that your expectation would be 9/16 of 556 would give you 312 round yellow seeds. You can see how we're kind of using a similar example to the salmon example. We have more categories and it's a slightly more complex example. And in this case, the degrees of freedom equal the number of rows in your table. So again, that's the number of groups. So we have 4 minus 1. And in this case, the number of columns minus 1, which would have been similar to the salmon example too, which would be 2 minus 1. And so 4 minus 1 times 2 minus 1 equals 3 degrees of freedom. Okay, so you can see the expected values are pretty close to the observed values. And so if you put all of these numbers into a chi-square equation, you would end up with a chi-square value of 0.47. Okay, so that's your calculated chi-square value. And then you would go to your table and determine your critical value of chi-square. Again, this time with degrees of freedom equals 3. And so if we go here, we see degrees of freedom equal 3. We follow it along. We would have needed a chi-square value of greater than 7.1 or 7.815 to reject the null hypothesis. And so in this case, Mendel peas actually, we can't reject the null hypothesis. So instead we accept the null hypothesis that the p-value is greater than 0.05 and the data actually fit the 9 to 3 to 3 to 1 expected ratio. Okay, so you can see how, and I haven't been very explicit about this yet, but the null hypothesis is that the data or the observed values are no different from the expected values. And so in the case of Mendelian genetics, you might want your data to match the expectation, and then you're upholding Mendel's laws of genetics and laws of inheritance. Okay, so this is kind of an example of when we don't want to reject the null hypothesis, and you can use statistics in this way. Okay, we'll go into another example, this time bird foraging, so more of an ecological example. Birds forage in a variety of habitats on the forest floor, in shrubs, and in trees, but do they forage the same way in different seasons? So here's a western tanager. This example uses what's called a contingency table approach. It's not exactly using a known expected value, okay? So that's what's different about a contingency table approach, is that you determine the expected values from the table itself. And so that's kind of how, I'll show you how that works. So if we go outside and we, in the spring, and then again in the fall, we observe birds and we count 32 birds foraging in trees in the spring, 18 birds in the shrubs, and only 5 birds on the ground in the springtime, compared to 12 birds in the trees in the fall, 24 in the shrubs, and 26 birds on the ground. Now we want to test, are birds foraging differently in the different seasons? So we look at the data, we might be like, yeah, maybe they're more in the trees in the spring and they're more on the ground in the fall, but we don't have any expected values in mind. So we use a slightly different approach. And again, we can't just look at the data and say, yes, they're doing things significantly differently. We have to run a statistical test. So what we do this time is we add up what are called row and column totals. And so we just literally add up all of the values for the spring. Okay, so 55 here, and all of the values for the fall, 62. And then we add up all the columns. So all the birds in the trees, all the birds in the shrubs, and all the birds on the ground. And then we add up all of the birds in the sample or in the study, 117. Now from these row and column totals, we can calculate expected values. And this is what's kind of cool, is we basically take the row totals here. You can see here the row totals and the column totals. And now each value, each expected value of y, or E sub I, is the row total for that cell times the column total divided by the overall sample size n. So for example, in this cell, birds in trees in the spring would be the row total for spring, 55, times the row total for birds and trees, 44, and then that quantity divided by the overall n, 117. So you can see that pattern repeating, 55 times 42, 55 times 31, 62 times 31, 62 times 42, and 62 times 44. And so that those numbers then in the boxes, after you calculate them, those become your expected values. And then you use the same equation, O minus E divided by E, or sorry, O minus E squared divided by E, and you add them all up for all 6 cells, okay? So here's this equation again, the sum for every value, I equals 1 to n, of every observed value, OI, minus every expected value for that cell, EI squared, divided by EI. And you add them all up for all 6 cells. And we'll talk about what happens when we come back. We'll learn about another type of test. So I guess before I leave, you would take this chi-square value that you've calculated, compare it to a table, and see whether or not birds forage significantly in the spring. And I'll let you save the results for the lab. Okay.